In this video I'm going to show you how to calculate animations from a Collada file. First I will explain the concept of an animation, then the math behind it, show some code example and where you can find all the relevant data in the Collada file. A virtual model consists of vertices. These vertices represent the mesh. To animate a mesh, we need to tell each vertex how to change its coordinates when animated. To define an animation, we need bones, or more precisely joints, that make up a skeleton that represents different poses within the animation. The position of the vertices change in relation to the position, rotation and scale of the joints they depend on. A vertex can depend on more than one joint at a time. To decide how much a vertex is influenced by a joint, we define weight values between 1 and 0. The animation itself consists of many different poses at different times, called keyframes. Each joint within a pose is represented by a 4x4 matrix. To get a pose between keyframes, we need to interpolate the matrices between these keyframes. The best way to interpolate those matrices is by using quaternions. With quaternions you avoid something called gimbal lock, which can occur using Euler rotations. But to keep this tutorial simple, I won't cover interpolation. This is a topic for another day and can also be easily implemented once you got basic animations running. The composition of joints can be considered as the skeleton. The relation between the joints are represented by a hierarchy. A joint can have one parent joint and multiple children joints. The pose of each joint is influenced by its parent and affects its children. The default pose of a joint when bound to the mesh is represented by a matrix called bind pose matrix. To calculate a different pose, we first need the inverse of the bind pose matrix to transform the affected vertex from model to joint space. This transform sets the joint as the origin of the vertex. Now we can rotate, translate and scale the vertex according to the joint's rotation, translation and scale. To get the new pose of the current joint, we need to include the pose changes of the parent joints in our calculation. To do that, we multiply the joint matrices of each joint along the hierarchy, starting with the very first joint. Now we can apply the final matrix in combination with the weight factor on our vertex. First I will show you how to do it in theory and then how it's done in practice. Let's take a look at the skinning equation found in the Collada specification at chapter 4.8. You can find all the links in the description. In the specification we can find the exact formula to multiply our matrices. We got our vertex, the bind shape matrix, the inverse bind pose matrix of joint I, the joint transformation matrix of joint I, and the weight factor of joint I. The bind shape matrix is usually only needed if the mesh has a different origin than the skeleton and is in our case just an identity matrix. The definition of the bind shape matrix can be found here. As you can see, we first multiply our vertex with the bind shape matrix, then with the inverse bind pose matrix, then the transformation matrix of our joint including its parent joints. At last we multiply everything with the weight factor. The inverse bind pose matrix is, like I said earlier, used to set the joint as the origin of the vertex. The joint transformation matrix represents the new pose of the current joint in relation to the new poses of its parent joints. The weight factor determines how much of the current joint's pose is taken into account for the new vertex position. In total, we do this calculation for all joints that influence our vertex. In this case twice, for the upper joint with 0.3 and the lower joint with 0.7, and don't forget to include the parent joints. This is what we would do in theory. In practice, we usually multiply the matrices inside our application first, then multiply the vertex with the final matrix and the weight factor inside our shader, as you can see in this example. Now let's have a look at what the code actually does. The equations above have we seen earlier. They describe the code you see down here. In this example, our vertex is influenced by joint 3 and joint 4 and can only be influenced by a maximum of 4 joints in total. First we define the transformed vertex, then we get the joint ID. With the ID we get the joint matrix and the weight factor that determines how much the current vertex is influenced by the current joint. Now we calculate the transformation of the vertex and add the result to the transformed vertex. We execute this loop for joint 3 and joint 4. The last iterations have a weight value of 0 and add nothing to the transformed vertex. At last we return the transformed vertex. When we apply a transformation to a vertex, we usually don't transform just the position, but also have to apply the transformation to the normal. This is done almost the exact same way, but this time we only use a 3x3 joint matrix because we only want to rotate the normal and don't change its position. One thing you have to consider though is that you maybe have to remove the weight factor, depending on if you are using flat or smooth shading for your normals. I also got 2 simple shapes available for download, so you can easily visually validate rotation and scaling within your animation. Now, after I have explained the concept, I will show you what data you need and where to find it inside the Collada file. First I will show you the mesh data and how it's composed of vertices. Collada files are in an XML format and consist of different nodes in a hierarchical order. The node containing the mesh data is named Library Geometries. Inside this node you find all the data a vertex is made of. For example, the position in 3D space, the normal, texture coordinate and color. Inside the triangles node you find the indices and the information on how to combine the positions, normals, texture coordinates and colors to a vertex. The input nodes tell you what type the index represents and the offset to the next index. Here you can see the indices in a single array. According to the index information, the first index represents the vertex. The source is the node with the ID human body mesh vertices, which you can find above. This node's semantic tag tells you that these are the positions and the ID of the source. Inside the source you find the array containing all the position data. Inside the accessor node you find information like the size of the array, the stride for each position vector and what the numbers represent. Each number is of type float, 3 floats represent a position and the first float of the stride is the x coordinate, the second and third are the y and z coordinate. The same principle applies for the normals, texture coordinates and color. Now that we know where to find what data, we can finally start composing the first vertex. The first number tells us that we need the position of the position array with the index 0. The offset tells us to move 1 step to get the index of the normal. The offset of the texture coordinates tells us that the index 2 steps from the start of our vertex is the index for the texture coordinates. We apply the same principle for the color index. With these 4 indices we got our first vertex put together. The order of each index set is also the order for drawing each vertex. The library controllers node contains the joint information of our model. A node with all our joints, the bind poses for each joint and the skin weights. The joints node tells us which source to use and what it means. The first tells us that the first source is the joints array. Inside the joints array we find all the joints by name. The second tells us that the second source holds the inverse bind matrices for the bind pose. The bind matrices are the matrices that represent the position, rotation and scale of each joint when the model was created and the skeleton was added. In other words, the matrices of the joints at the time of the default pose. Later we have to use these inverse bind matrices in our calculations to transform the affected vertex from model space to joint space, like I explained before. To build a matrix, we have to read the array with a stride of 16. 16 because our matrices are defined as 4x4 matrices of floating point values. Matrices are written in row major order, as stated in the Collada Specification. This means that the first 4 floats make up the first row of the matrix, the next for the second row, and so on. Inside vertex weights are arrays of indices that tell us which weight belongs to which joint and vertex and what offset to use. vCount contains the joint and weight indices. The first index of a set refers to a joint, the second to a weight value. V contains the index of the vertex that the index set of joints and weights belong to. So the first index set with joint 3 and weight 3 belong to the vertex with index 0, and so on. To set up the joint hierarchy, you need to go to Library Visual Scenes. Here you find all the nodes that make up the visual scene in a tree-like structure. Nodes of type joint are what we are looking for. The SID tells us which joint it represents. It contains the name of the joint we previously extracted from the joint array in library controllers. You can see that the hierarchy starts with the torso joint, followed by shoulders, neck and legs as child nodes. If you follow the tree structure, you will find the remaining joints. This way you can set up the hierarchy inside your code. At last we have to extract the animation data. Inside library animations and the animation node of our armature are all joints listed that are animated. In our case, only the left shoulder, left upper arm and left lower arm. Their child nodes consist of source nodes and the sampler that tells us what type of source. Here we can see the first node is of type input with an array of floats. These floats are the keyframes of our animation. The second source is of type output with an array of floats that represent a 4x4 matrix. These are the pose matrices for each keyframe. They are linked in the same order as they occur in the arrays. The first matrix for keyframe 0, and so on. The third source tells us how to interpolate between each keyframe. In this case, all our keyframes have linear interpolation. At last I want to show you a tip that helped me when I encountered problems displaying animations and that possibly could have saved me hours of debugging. If your calculations seem correct but your model still looks weird, go inside Blender, make sure you are in object mode, then hit Ctrl A or click on Object and then on Apply and select all transforms. A way to make sure your model is correct is to import your Collada file into your Blender scene again. If Blender displays everything correctly, you can exclude any errors within the export or animation process. I also can highly recommend the tutorials and sources I've linked in the description.